it is a parabolic reflector like a mirror, so it reflects and goes to the focal point. Very simple actually, right? And then in this focal point you have some sort of receiver in the sense that you have some element which can convert this electromagnetic signal, right, electromagnetic radiation into electric signal, right? All the circuits understands electric signal, right, that we can detect, correct, using our instruments. And then you can take this signal down and do further processing, correct? Great. Now if we think of this thing, this is like a single pixel, right? We were discussing yesterday that so it's basically when all the radiation comes in, so it's like one spot, right? Even if you think of it in like a lens, right? One parallel rays comes, one spot, correct? Now if some other parallel rays come, say for example you have one point, right, one star which is at infinity, parallel rays are coming, so here you will get one star. Now then you have some other star which is a little bit down, so their parallel rays will be a little bit like this, and there will be some spot over here which is a little bit shifted than this. So you need multiple pixels to do that, correct? One pixel will not do. But here, unfortunately, as I said, that these pixels are big. You cannot put like 100, even like 128 by 120 is a dim. But now, yes, I mean there are possibilities. I'll come later to that. So this is typically the situation. And there are some multi-pixel feeds, okay. So this is like this Sparks multi-beam receiver. You see there are multiple spots. Each of them actually can behave like a single different pixel. So effectively you are saying that I will actually can look at a larger portion of the sky. So if some star is a little bit down, I can still see that using some other pixel over here, right? Then this is again ASCAP phased array feed, which has again like multiple pixel. As you can see, there are many pixels, right? But then these technologies are like, it's hard to do, okay. When I say hard, trust me, it is hard to do, okay. But anyway, so people have done with limited success. ASCAP, this phased array feed is still running and it's taking observation, okay. Now let us take a look at the signal chain, right? We are all like trying to say that okay, we need to detect, fantastic, right? So this is the front end, right, which I have shown here, this guy, right, this guy. So now the typical electromagnetic field, right, this light and all these things, right, so it generates. So when it falls on so what it is basically an oscillating electric field. It's an oscillating electric field. It's a real electric field and a magnetic field perpendicular to each other. Now what happens if there is a conductor and this guy falls on it? Electric field will push the electrons, right? So what does it mean? When this electric field actually falls on a conductor and then it tries to push the electron, so the electron will accumulate in one side, right? So it will develop a potential, correct? That potential will actually lead to a current. Now let us think about, so this current is actually very feeble. As I said that the signal is very weak, okay. Can anybody give me a number like I have like simple conductor and some radiation, let's say from this room is kind of falling, like what is the expected voltage to be developed? Take a wild guess. Millivolt? Micro? Yeah, it's actually less than microvolt, right? So now when we are talking about this much feeble voltage, you cannot transport this guy because the power is very, very low, right? And the power losses through the cables are very high, right? So this will die, this current will die. You 1 meter bhi leke jaoge to ho jayega, done, right? So we need to have an amplifier over here, which will amplify and sitting right there because you cannot transport this guy, right? So if you look carefully, all telescopes, okay, if you look carefully, all telescopes there, so this is called feed, okay, this part is called feed, and there you will see an amplifier, low noise amplifier sitting right next to it, okay, right? Then here comes, right? Now you see the signal which is coming from the sky, let's say star, right? Yesterday we have learnt about stars, right? And there What kind of spectrum we expect from a star? Black body. What does black body means? All frequency, right? From here to everywhere, right? So the signal which is coming from the source, you know, they are broadband signal, really, really broad, correct? But are we interested in all those frequencies? Yes, to some extent, right? But at a particular time when you are designing the telescope, we must focus on a particular frequency range, otherwise everything will mix up, right? If you have a detector which can which can respond from 0 megahertz to, let's say, 230 gigahertz, then it's like, when you get the signal, it's like all mixed up, right? So here you have a band pass filter. What it does, it basically select a part of the frequency which you are interested in, right? Fantastic. So then all the unwanted signal for the time being got filtered out. Now you have a band where, like, only the interested signal is there. Now let us talk about, let's say, if we consider GMRT, right? So GMRT works at, like, from 150 megahertz to like 1.5 gigahertz, correct? Now I have a signal which I am, let's say, interested, like H1 21 centimeter signal, right? So yesterday we have seen H1 21 centimeter is like 1.4 gigahertz, 1.4 gigahertz signal. So if I want to detect it, so I have to tune my this whole system to 1.4 gigahertz, right? Now, as Jagdeep was also mentioning, if I want to detect a signal at 1.4 gigahertz, right? If I want to reconstruct it, so how much, at what frequency my sampler should be running? Plus minus क्या है? Greater than 2.8 gigahertz, right? Nyquist sampling is 2 times the maximum frequency present. Maximum frequency I'm trying 1.4 gigahertz, right? So 2.8 gigahertz, let's say 3 gigahertz. Okay? What is the speed of our processors in our computers? 2.2 gigahertz, 2.3 gigahertz. If you put turbo, it may reach up to 3 gigahertz, right? Now think of it, that the fastest chip you have running at 2.2 gigahertz, you want to deal, and as he said, that you have to discretize, right? And collect these discrete values, write somewhere, by hand you cannot do, right? So you have to have a clock which will send a train of signals that will go and hit, A to D will work. So you are having a system of 2.2 gigahertz trying to address trying to sample a system at 3 gigahertz. A little bit, seems a bit difficult, right? There is way out. Okay. So what we are interested in? We are interested in, let's say I have a sine wave at 1.4 gigahertz sitting. I am not interested, like, I am interested in that nature of this, ups and down, right? It's really, I don't care, like, at what frequency it is sitting, right? So there, what I can do is that I can mix that signal with a locally created signal. So let's say I have a signal. इसको खोलो थोड़ा. हाँ? ठीक है इधर. Leave it. It's fine. Don't worry. So let's say I have a signal A cos of omega t, right? This is coming from the sky. Okay, no problem. Simple sinusoid signal. Life is simple. Then I want to mix with, like, A1 cos of omega 0 t. This I can generate with my local oscillator. I have an instrument which can, signal generator, simple. Now a mixer which can do this. A into A1 cos of omega t, cos of omega not t, cos A cos B. What is the formula? Cos of a plus b plus cos of a minus b. इतना difficult क्या है? So this will be whatever a1 a cos of omega plus omega naught plus cos of omega minus omega naught t. Yes, half. Alright, this is fine. Now think of this thing. If I could mix this thing, correct? I am getting one component with high frequency and one component with a difference frequency, right? Now this part will still come over here, right? Now when the signal is coming from the sky, right? This part is actually important, that how much is the power. See, this is just a sinusoid, right? Correct? So effectively what I am saying, somehow if I put a high pass filter, you know, a filter which can get this guy out or attenuate this guy, sorry, I will place a low pass filter, so it will only pass low frequency, that is this, correct? And this part it will attenuate, right? So if this is at 1.4 gigahertz, that is my H1 signal, 1.4 gigahertz, that is omega, correct? Right? Let us mix this guy with 1.39 gigahertz, correct? So this is 1.4 minus 1.39, right? So what is the difference? 0.01 megahertz, right? Gigahertz. So this is about 10 megahertz, right? 10 megahertz. Now can you sample this guy? Right? Now our processor can actually handle this thing, right? So that is why you see this mixer is sitting there, and this pass filter, it is basically filtering out that high pass component, this one, right? And then it comes to an, another level of amplification, and then forget about this part actually people used to do earlier. Now most of them, they don't do this, okay? So effectively you are mixing the signal to make that RF frequency to a frequency which you can handle, right? And that is, this process is called heterodyning, okay? So this one experiment you will actually do on this next week, right? So now with this, now I am talking about, okay, the signal is coming, and then, it will come, will filter, then this current, this voltage, whatever is coming, then I will have a sampler, I will sample and then go, right? Fair enough. But the problem is that if the signal is very feeble, see, if you have power, lots of power, right? You can see the nice peak, do Fourier transform, everything is fine, not a problem. But then, if the signals are very weak, it's like almost zero, right? Then there are problems. I'll tell you. So one Jansky source is a bright source in the sky. But do you know what is the power of one Jansky source? 10 to the power minus 26 watt per meter square. We talk about like milliwatt, microwatt, nanowatt. Nanowatt is 10 to the power minus 9. Do it like 3 times. Nanowatts cube, right? See, that is the kind of, and that is one Jansky source is like very bright source. We detect like micro Jansky source. So micro Jansky means 10 to the power minus 32, right? So if I have a 4 meter dish, what is the area of 4 meter dish? Like 4 meter diameter, so it's like 50 kaise hoga? 2 meter is the radius, right? So it's like pi r square, right? So 3 into 4, 12 meter square, right? So we have actually just behind the guest house, you will see we have a 4 meter dish. We have 4 meter dishes, right? Now this 4 meter dish, right, having a 12 meter square area, so 12 into 10 to the power minus 26. That is the Jansky source, right? So how much power you are going to get? It's very difficult. So that is why the signal in radio astronomy, okay, they are basically noise. They are noise. Effectively, the signal is there, but they are noise. Okay. So the phases of the incoming signals are random and band limited. Okay, so this is one important aspect. So where the signal is coming from? It is coming from stars and everything, right? All the astronomical big sources, right? Now, the incoming signal, whatever is coming, this time, whatever is the electromagnetic wave, and some next time, these guys will not be correlated, because in stars there are like thousands of random things going on. It means there is no coherence as such. There is a very, so basically if I know at this moment, the next moment phase will not be correlated, because the process in the next moment has completely randomized, right? If you have only a thing which is like consistent with each other, then only it will have a maintain the consistency in the phase, right? So these signals are originated by stationary random process. So this is one of the very important aspect I would like to explain. Stationary means I am saying it is noise-like, but the character of this noise does not change. How do we characterize noise? It should have a mean. Like noise means what? It's a Gaussian, random Gaussian distribution. Noise means what? Random. You do not know what is coming next, right? Fair enough. But if you have like 1,000 of samples, you can have a mean, you can have a standard deviation, right? I can say that my mean and standard deviation does not change over time, right? It's still random. I can like have one, the next sample is still random, but their collective mean is not changing. Okay, so this is actually true for astronomical processes, except pulsar, leave the pulsars apart. Because the astronomical sources do not change over even our lifetime. Okay, you measure a source like 1 Jansky and ask your grandson to measure it again after maybe 200 years. Okay, it will be the same. Because within that time does not change. So we can fairly assume that these signals are basically stationary signals. Means they are noise-like, but their character do not change. Yeah? Fantastic. Okay, so before just going into the next level, I would like to kind of give you a bit kind of introduction to two techniques. Okay, kindly update me on the time. Okay, I will. What is the 1 o'clock? So 15 minutes. Let's see. So I will skip this Parseval theorem. I will directly come to the convolution. Okay. So convolution is a very important aspect in you will keep encountering in different places. Radio astronomy to for sure, right? So you see, this is the mathematical kind of expression for it. This is how we are defining it. Okay, physically what it means I will tell you. So I have two functions. One function f1x. Okay, this is a running variable, right? U. So f1u, and then you have another function f2u. Okay. What I am doing is that I am shifting this function, you see, f2 by some amount x, right? I have one function, I have second function. I am shifting this function by some amount, multiplying these two guys and add. Okay, so this is you can think of it this way, that it's actually not difficult, but it is important to kind of. So I have, let's say, one function like this, okay, and a function like this. This also is a function, right? Jagdeep mentioned delta function, correct? So this is my f1, this is f2. So what I will do is that, let's say I have to calculate g of 2, let's say. So what is the difference? Difference would be 2, right? So I will shift this guy by 2, multiply these 2, and sum, integrate the whole thing. Integrate means minus from here to here, right? If I have to calculate 3, so I shift this function by 3, multiply, add, correct? You are getting my point, right? I will give you one example, you will understand. Let's say lens experiment you people have done, right, at some point, right? You know, take the lens, put it in the sun, and there is a spot, right? Now, remind me once, you guys have learned the ray optics, right? Right? What does it says? That if you focus the rays, it should go and meet at a point. What is the area of the point? Area of the point is? Area of the point is? Area of the point is 0, almost 0, right? Near to 0, right? What would be the energy density if the point area is going to 0? Energy density is like total energy divided by area? Infinity. If the energy density is infinity, if you put your hand, right? Does it do? No, right? Then it means that it has a finite size. That is not 0. And that actually you can see also, there is a finite spot, correct? It means, so it is coming from diffraction, forget about it, but let us look at this picture. So I have a one star, kind of, parallel ray coming, same scenario. I will get a spot over here. I will not get a infinitesimally small point, right? One point. I have another star just below that, correct? So think of it. I have one spot, correct? Then I have a next star over here. So I have another spot, right? Another star over here. I have another spot, correct? Now think of it this. Let's say this is my F2. That is the spot size. And this is my F1. That is a summation of 3 delta functions, correct? This multiply and sum. Delta function, if you multiply this function with the same function comes back. So this will come over here, this will come over here, this will come over here, right? Isn't it exactly convolution? F1 into F2 with some shift and integration. Just think of it. It is a convolution. Okay. So if you look at it, so this is the mathematical description. I'll just, because of interest of time, I will just quickly run through. So one very important property of the convolution is that there are two functions. If you take the Fourier transform of convolution, they are basically in the Fourier domain, they are multiplication. It means if you take a Fourier transform over here, so a Fourier transform this multiplied by Fourier transform this. Okay, so this will come back. Then autocorrelation. So correlation is basically multiplication of two signals, right? So I have a signal F1 and then I have a signal F2. It is very similar to the convolution except this guy, the complex conjugate. Okay. Here also you see I am shifting the signal, multiplying and integrating, but with a complex conjugate, correct? So this is how the correlation is defined. It is like, I have one train of signal coming in one antenna, another train of signal is coming in the another antenna, right? So I can shift them, multiply and add them, right? I can do all these operations actually on the data, correct? In fact, people do it in the radio interferometer, the correlator somebody asked. Actually, these operations are done, right? Now, if you look at this G, that we are defining it like this. Now, if you think of it like, see, now I have this F1 cross correlation with F2, right? If I take a Fourier transform, you see this is like, it is exactly the same as convolution except with this star, correct? So this can be considered the convolution of this guy and this guy. Yeah? Are all gone, right? Think of it instead of F1 star, just consider that F1 star itself is a function, right? Then this is a convolution of f1 star and f2. Yes, fantastic. Take a Fourier transform of G. Then Fourier transform of f1 star multiplied by Fourier transform of f2. Right? Fourier transform of f1 star is like f1 star, Fourier transform star. Right? This and this is f2. Correct? Now, autocorrelation is what? Auto means you are multiplying same with same signal but with a shift. Correct? So, in autocorrelation this f1 and f2 will be the same. Yes? If it is same, then this f1 and f2 will be the same. So, if you put f1 here and f1 over here, so it is like f1 star f1. Correct? Mathematically there is no problem. So, what does f1 star f1 means? Mod of f1 square. Correct? Right. Now, if I consider this x as t, my time, right? If we consider this x as time, then what you expect over this s to be? Frequency. People know like how it comes, right? If you look at the Fourier transform equation, this is basically, this s is like, the dimension of s is actually 1 upon x. 1 upon x. So if x is t, then this has to be 1 upon t. That is frequency. Correct. Now let us look. So this is f also is a function, right? See, this is a function. What is this function? This is basically the wave train which is coming. Right? If it is like a single sinusoidal, so you would expect like this. Right? So this is a function. Then if you do a Fourier transform, this is also a function. Correct? And what this means? This means that this f of s square, that is basically telling about how much power is there, and power as a function of frequency. Correct? So this square, f of s square, is basically telling you about power, spectral energy density. What do we mean by spectral energy density? That how much power is there at every frequency. Now remember the black-body curve. What the black-body curve says? Is that specific intensity as a function of frequency or lambda. What is specific intensity? That is a representative of power. Right? So now if you can, now remember, look at the left hand side. Left hand side is our measurement. That is that wave train which I have sampled. Correct? And what is the right hand side? Right hand side is the power spectral density which actually directly connects to the source. Right? Now if I can measure this left hand side with a my telescope, and then I do a autocorrelation, and whatever we have done over here is that we have done the autocorrelation, correct, and taken a Fourier transform, right? Autocorrelation, taken a Fourier transform, and I have reached over here. So it means I have a telescope which can record signal as a function of time, take it, do an autocorrelation, and do a Fourier transform. Then I get the power spectral density, correct? And then you can tell me whether this source is a black-body radiating source, or it is a non-thermal synchrotron radiating source, or it is a free radiation emitting source or something, right? This is how it is done. Okay. So now very quickly what I will do is that, so this is the autocorrelation connects to the power spectral density, right? But we were discussing about the signal, right? So this signal is X, which is like a random signal, as I said, that it is, the radio astronomy signal is actually noise, correct? So this noise will have some expectation value, correct? So expectation value of X is like X into Px dx. We have all learned this thing, right? P is the probability distribution. Yeah? So in case of a Gaussian noise thing, we will just put Gaussian over here. So now expected value of fx will be like simply like fx instead of x, correct? And then variance will be expected value of x square minus square of expected value, right? This is the definition, correct? Now let us look that if such signal coming from the sky, what happens if we do this? Yeah. So let us say I have a linear detector. Linear detector means, I'll tell you what it is. Okay, sorry, I'll skip this thing. I can't skip these things. Bad luck. Yeah, how much time is it? 1:10 na? Okay, ठीक है. Okay, I will try to do this.